All right, so hello everyone. Thanks very much to Thierry, and I'd like to first of all say thanks very much to the organisers of this conference for inviting me to speak. It's really a great pleasure to be here. So my talk might be a little bit different in some ways from other people's talks because it's not related to engineering or physical sciences, and it's related to something called composite indicators. And I thought maybe a good way to start would be to ask, who here has not heard of composite indicators or doesn't know what composite indicators is? Could you raise your hand if you don't know what a composite indicator is? Yeah, so a reasonable number of people. Let's have a look. Well, composite indicators is a term that we use for all these different types of rankings that you can see here. So I imagine that after seeing some of these names, some of the people that just raised their hands might realize what a composite indicator is. Sorry. So, yeah, it's things like university rankings, the Global Innovation Index, the Better Life Index, all these kinds of things. Now, just to set up for the end of the presentation, I'm going to talk about two particular composite indicators, and these are university rankings. So the two that I'm going to talk about are the Times Higher Education ranking and the QS World University rankings. And I imagine a fair number of people might have heard of these two composite indicators. But anyway, we'll come back to them towards the end of the presentation. So to start off with, I would define what a composite indicator is. And the best definition that I can think of is that they are aggregations of observable variables which aim to quantify non-measurable concepts. So let's examine a little bit what that might mean. Well, first of all, what do I mean by a non-measurable concept? Well, the easiest way to explain possibly is just to take a few examples. So if we look at the Financial Secrecy Index, for example, it's an index that aims to measure the financial secrecy of countries around the world. So that's not something that you can go out and measure by doing some kind of experiments. And what financial secrecy means might be different from, defined differently from one person to another person. Same goes for the Global Slavery Index, which aims to measure slavery in countries, or the Better Life Index, which is an index by the OECD on quality of life. So the reason that people build these things is mainly to quantify, as I say, things that are quite hard to quantify and have no particularly concrete definition. They allow you to aggregate a large number of variables or indicators into an easily digestible format, so it's something that can be interpreted by absolutely anyone. It just boils down to one number at the end of the day. And it allows you to give simple comparisons between countries or between universities. So, sorry, no, I should have pressed the button. Let's have a look at how a composite indicator looks underneath. Composite indicator is, all it is really is just, you have some indicators, which in this case are the blue boxes along the bottom, and they aggregate them into groups or subgroups of indicators, and those subgroups are aggregated finally into the final index itself. So you can see in this case, this is the Global Innovation Index, and you can see the kind of indicators that go into this. Now, throughout the talk, just to introduce my notation, it should be very easy for everyone to follow, but it's just Y is the output of the composite indicator, which is the number, the final number, and the XI are just the indicators that go into it, okay? Now, I think most people here might be slightly horrified in a way to learn that all a composite indicator is simply a weighted average, with some exceptions, of these indicators. So that's all it is. So when you come from a background like I do, which is mechanical engineering, and you've dealt with finite element models and CFD models, and then you encounter something like this, which is really just the weighted sum of these these indicators, it looks very, very simple, and it is in many ways. But there are also many other things going on behind the scenes. So all we have is a weight W, which is multiplied by each indicator. So just to summarize, the composite indicators are simple aggregations of indicators, and I put a star there because actually they're not really that simple. There's a lot of statistical analysis that goes into them, and particularly the conceptual framework is something that is very difficult to get right, which means choosing the right indicators and justifying and so on. So there is a sort of whole methodology behind this. It's not as simple as just adding them up. But they're simple in many ways. They're very, very subjective because, of course, what one person means by innovation might differ massively from what another person means, and there are many subjective decisions that you make when you build these things. And they're very uncertain as a result. So the real kicker is that they actually attract a lot of public, political, media attention, which means that it's important to really have a look at these things closely because in some cases lots of decisions are made based on these composite indicators, even sort of political decisions, management decisions, and so on. So they're interesting to look at for that reason. So my talk's going to focus, there are many things that go into a composite indicator, but I'm going to focus on this weight term here. So one of the first things you might think, okay, how do I actually choose the weights that go into this weighted average? Okay. Now, the Stiglitz report in 2010, which was a report made after the financial crisis, one of the conclusions that it identified was related to composite indicators. And it said that the general criticism of composite indicators is the arbitrary character of the procedures used to weight their various components. Okay, so this is something that's quite well known. These weighting techniques are not particularly transparent or not well explained in some way. So how do people weight composite indicators? Well, there's two main ways to weight them, and I won't explain in very much detail, but one way to look at it is to assign the weights by a sort of degree of belief. So you might say that, for example, one indicator you assume is twice as important as another indicator. Therefore, you might assign twice the weight to that indicator as to the other one. Or you might assume that they're all equal, so you would weight them all equally, okay? So these are kind of based on your belief of how important these indicators are, and there's a number of more complicated ways of looking at it, but it boils down to the same thing. A second way to weight composite indicators is based on statistical models, things like principal component analysis, data envelopment analysis, so a little bit more sophisticated, but these methods are not really used in the big visible composite indicators, for example, the ones that I showed on the first slide. So these tend to apply for more sort of technical ones that are used in, for example, management or performance management scenarios. So I'm going to focus on the first group. So people tend to assign these weights based on importance, but one thing that we've known for a while is sort of not known, let's say, by a lot of people in the composite indicator community, but certainly a certain number of people know that these weights don't actually translate to importance, okay? So I can explain why this is. Some people might already have figured it out. If we look at an example, and I think I might have stolen this example off Andrea originally. I'm not sure if you came up with Andrea. Anyway, this is or maybe it was Paolo. Imagine that you have a composite indicator to rank teachers at a university. So you want to rank your teachers or give them a score in some way. One way that you might do that would be to take three indicators. One which might be the number of publications, one might be teaching feedback, and one might be the hours of teaching. These could be anything really. So following a sort of standard composite indicator methodology, you take the weighted average of the three indicators, okay? And you give them equal weights. Now, it's the only thing I didn't really mention was one thing you do is you actually normalize all the indicators before you take this average. So they're all on the same scale, which may be between 0 and 1, let's say. Okay, so they're all normalized, these three indicators. But it turns out that there's a correlation or a dependence between two of your indicators in this toy example, okay? So I say that there's between x2 and x3, there's a correlation of 0.7. One way we can measure the influence of these indicators on the composite is to take an R² value of each indicator, okay? So if we do that, we find the following results, which show that the first indicator has a much lower influence in terms of the R² value than the other two. And that's because, of course, the other two are correlated. So, you can imagine the dilemma of the dean that might be making this indicator. He might think, okay, I should then increase the weight of x1, right, to make up for the shortfall. But of course, if someone looks at the formula without really thinking about it, they will complain, why is it that you're favoring publication so much more than the other variables? Okay, so there's this sort of communication problem. And correlations are extremely common in composite indicators. It's the norm rather than the exception. So if we know that importance isn't equal to the weights, how can we measure importance? Well, one way we already discussed, and that is to use something like R², which is just a linear measure of dependence between each indicator and the composite, okay? And this is fine, but maybe it's not a linear relationship. So you can probably see where this is going. This is where the sensitivity analysis starts to come in. So of course, SI, the first order sensitivity index, is, as Elmar noted, is actually the nonlinear R² through a scatter plot of your data, okay? And I'm going to use the term correlation ratio because first of all, maybe not everyone might know, but actually this measure was first conceived by a guy called Carl Pearson in 1905, so that's actually originally where it comes from. But also because I'm not using it in the context of a variance decomposition. I'm using it as a measure of nonlinear dependence, so it's a slightly different use. I'm not trying to decompose any kind of variance here, I'm just looking at a nonlinear relationship. So we can estimate this via nonlinear regression. To show you how this works, you simply make a scatter plot of your data, one of your variables, xi. You plot y against xi, and you end up with something like this. Now, if you fit a nonlinear or linear, well, nonlinear really, regression through this data, that gives you the main effect, which is the green term up the top there. If you know the main effect, then you can calculate SI, okay? So it's quite straightforward. Now, you might possibly be thinking at this point, why would it be nonlinear if we just got a simple additive model? Well, the thing is that the nonlinearity comes not from the structure of the model, but from the dependence structure between the variables, because the main effect is conditional, is taken with respect to x tilde I. So it takes the joint distribution of x tilde I into account. If there's a dependence or if there's a skew or something like that, it can produce a nonlinear main effect, okay? So we need a nonlinear regression approach. Just to clarify, in order to actually calculate SI from the main effect, you simply take the fitted values of the curve, which is the y hat j, and you take the variance of them, essentially, which is the variance of the line, in a sense, at the points, the xi points, sorry, the xj points, and you standardize that by the variance, okay? So it's just a simple computational variance formula. Now, the nice thing about using this kind of approach is that you can get estimates of SI in the case where you've got dependence between your variables. But you don't need to know any of the distributions. You just need the scatter plots, okay? So you need the sampling to be taken with respect to the distributions, the joint distribution, but you don't need to know any analytical form of the probability distribution, okay? And so the distributions can be arbitrary. And actually in sensitivity analysis, this approach was is written up in a paper by Davega, I think it was in 2008 or 2009 or something like that. So it's been around for a few years in sensitivity analysis, this idea with dependent inputs. So how do you get these nonlinear regression curves? Well, I use three methods just to sort of make a comparison and see if there's any difference. So the first thing I use is penalized splines. So penalized spline looks a bit like this. You've got a polynomial term, so that's just a pth order polynomial. Don't forget, this is just a univariate regression, so we're not in multi-dimensional situation here. And then you've also got a spline part. So this is a sum of k spline basis functions which are located at different knots, and splines are just pieces of polynomial functions, okay? So if you look at that, you can see it's actually linear in the parameters. So you can actually get estimates of the coefficients just with a standard linear regression estimate, ordinary least squares. But if you do that, then you'll find that you overfit the data. So what you actually do in practice is you set a restriction on the estimator, and that results in a kind of smoothing term which weights between the polynomial part and the spline part and gives you a really nice fit through the data. So you end up with something nice looking like that in general, okay? And the nice thing about splines is that they're very fast to fit. Because they're linear, almost, you can use a lot of the properties of linear regression to get your estimates, and you can fit it very, very fast. Like you need a cross-validation measure, for example, and that can be calculated extremely quickly with linear regression methods, okay? Anyway, that's one tool. The second tool is local linear regression. So all that is, and this is actually local mean regression that I've put here because it's a lot easier to write out than the full local linear term. But all it is you've basically got this weight function, it's a kernel function, which is based on the distance between xi, so some point in x, and it basically takes the average of the output values, yj, but the average is weighted by the distance away from the point that you're trying to estimate. So points further away have less influence than points that are close together. And it's just then normalized by the total sum of the weights. And I found this nice graphic on the internet which illustrates it really nicely. You can see basically the linear trend is just taking into account the points nearest to it, okay? And I have to give credit to where I found it because it certainly wasn't me that made that. So that's another method. And then I finally just mentioned the Gaussian processes quickly, which have already been talked about. A Gaussian process just has a mean function and a covariance function, and you update it condition it on the data, and you can estimate the hyperparameters, or you can use a Bayesian approach. And the important thing here is that I'm using a noise. Do I circle it? No. The sigma n in the corner there is basically a noise term, which basically means that the Gaussian process doesn't interpolate through the points, so it smooths the points, which is exactly what I want in this context, because I don't want to join all the dots. I want a nice smooth line through the data. And there's a little graphic again which shows you how the Gaussian process fits as it encounters more data points. So the reason I use the Gaussian process as well is because if we use MCMC to fit the Gaussian process, and admittedly you could do this on other methods as well, you can get every time, once you've burned in your MC-MC chain, you can, for every MC-MC estimate, which is a sample from your distribution of parameters, posterior distribution, you can estimate, plot a main effect line through your data. And using that line, you can get SI. So what that means is that you can get a distribution over SI, which takes into account the uncertainty in the parameters. So it's kind of gives you some confidence intervals, basically. So that's one thing, okay? And then I was thinking, okay, can we go a little bit further with this, okay? So I kind of thought it was a bit like going down a rabbit hole, and then I found this nice picture. That's why it's there. Now, Sergey mentioned that about correlated sensitivity analysis, and he touched on the fact that sometimes people separate sensitivity indices into a correlated and uncorrelated part. And this idea has been around for some years now in the literature, that in a correlated sensitivity analysis case, you can have the correlation ratio, or the first order sensitivity index, and you can decompose that into a sum, which is the sum of an uncorrelated part and a correlated part, okay? In the context of composite indicators, why would we want to do that? Well, one reason might be that you would reveal variables that could actually be removed, because if the uncorrelated contribution is quite low, that would mean that the information in that variable is already contained in other variables anyway. So there's not really much point in it being there in some senses. And the other thing is, it will reveal to you variables which are insensitive, relatively insensitive to changes in weights, because if you change the weight of a variable, you're just affecting the uncorrelated part, not the correlated part. So you, in a sense, the correlated or the uncorrelated SI is a kind of measure of sensitivity to weights in some strange sense. So there might be lots of ways that you could, explore this in terms of composite indicators. So just to explain how I actually get those measures, well, if we take a very simple example where we've only got two inputs, x1 and x2, if you plot x1 against x2 or x2 against x1, you'll see some kind of relationship like that, which indicates you've got a dependence between the two variables. If you can estimate that dependence as a kind of function, right? So one way is just to draw a straight line through that data. If you then subtract the straight line, the fit basically, from your data points, it kind of gives you this, it kind of like orthogonalizes the data. So it sort of removes the dependence in some way of x2 on x1, okay? So this kind of gives you like a sample that is now uncorrelated between those two variables. In the more general case, you're not regressing one variable on one variable. You would actually regress xi on x tilde I, so you're doing a multivariate regression. And this idea, at least in the context of sensitivity analysis, was proposed, I think, first by Zhu and Gertner, which is a paper in 2000, again, somewhere around 2008 or something like that, 2000 something. And they use a sort of linear regression basically to remove this dependence, okay? So if you, just to show you slightly more formally, all it is a linear regression, and then you take the difference between the two and you end up with this z hat I, which is somehow like the uncorrelated xi in a sense. And if you now regress y on xi in the same way that we were doing before with the nonlinear regressions, we get now an SI using this new uncorrelated sample, independent sample. I'm not sure if that's exactly the right terminology, to get the uncorrelated SI, okay? And of course, knowing the sum of the two adds up to SI, we can find the correlated part simply by subtraction. You can extend this idea to nonlinear dependence between variables if you think that might be a good idea. So, you know, it seems natural in a way to assume, okay, if you do a linear regression, in general, you're just looking at pairwise dependence, pairwise linear dependence, okay? Perhaps there's no reason why you couldn't extend that to something a little bit more complicated and use a multivariate nonlinear regression like a Gaussian process or something similar, which would then hopefully kind of model a full order dependence, nonlinear dependence between variables, okay? You know, whether that's justified or not, I don't know, but it's something that I investigated. So that was sort of part 2, and then the final part of the kind of methodology, before I get onto the example, is about I mean, you might think, okay, so we now know a lot about the real influence of these indicators. The natural question is, okay, can we now adjust the weights so that we actually get the real influence that we really want? Okay. So the way that I thought of doing this is really just a kind of brute force approach based on optimization algorithm. So there's a paper that investigated a lot of this stuff, which by a colleague of mine, Paolo Paruolo, and also Andrea was a co-author. And in their paper, they do an optimization like this, but it's just using a linear, sort of linear regression, linear properties. So they do it analytically. This is like a little bit uglier, but at least it takes into account the non-linear part. You know, whether that makes a huge difference, I don't know. But anyway, this is the way I'm doing it. So in this kind of diagram, the thing that we're interested in is this target SI. So the target SI is the importance of each the true importance of each indicator that we want to obtain using our weights. Okay. Now, actually what we're doing is, so this target SI we set as the original weights of the developers. So if you imagine you see a composite indicator where a variable is weighted 30% and another one's weighted 40%, okay, and so on, you assume that that's the sort of ratio of importance that these developers are interested in, okay? So in terms of SI, so these weights always sum to 1, okay? SI in the correlated case doesn't sum to 1, it will be more than 1. But all I do is I just normalize it by dividing by the sum of SI, okay? Which might sound a bit naughty in kind of variance decomposition terms, but I'm only scaling it so I can make it comparable with the weights, okay? So it's a simple approach. You just take a set of trial weights, which may be the original weights, or equal weights, let's say. You do your nonlinear regression, and that gives you estimates of SI for each variable. And then you just take the difference between all the SI that you estimated and the target SI, which you're trying to get. And basically, that kind of gives you an objective function, which is a function of the weights, okay? And of course, you want to minimize this difference. So if we look, if we write that down, we've got, we're just looking for the minimum of this sum of the squared differences between the target, the SI star, and I've starred them to sort of indicate that they're normalized, between the SI that you calculate. The tilde is normalized and the star is the target, okay? And of course, the SI is a function of the weights. And you can use, your favorite nonlinear or favorite global optimization algorithm to find this solution. It's not that difficult. It doesn't seem to be that difficult an optimization problem from my experience. So let's just go back over this, because maybe it might seem a bit sort of meandering in some way. We've got kind of 3 components here. One is to use SI, the first order sensitivity index, the correlation ratio, to estimate the importance of each indicator in the composite. And we do that with nonlinear regression. The second thing we can do is to separate the correlated part from the uncorrelated part using this kind of, again, some regression approach. And the third thing we can do is to try to adjust the weights so that we get the importance that we are after, or whatever importance we desire. Okay. So back to the beginning. So these are maybe the two most popular university rankings. I imagine most people here have come across them at one point or another. You might not have chosen your university taking this into account, but I think these are quite influential, and also the managers of universities, the deans, the management of the university, I think they kind of worry a little bit about these rankings, if they're too high or too low, and there are plenty of stories about the media and about even governments have sacked people based on these rankings and so on. So they're quite influential, which is why they're interesting, I think. So let's just look a little bit at what goes on in these rankings. Well, the QS ranking, which the #1 hit in Google, by the way, if you type in university rankings, it's got 6 indicators. One's based on academic reputation, which is a survey, and it's got a weight of 40%. Another one on employer reputation, again, it's a survey. Faculty, it's basically a teacher to student ratio indicator. Citations, international faculty, and the number of international students. So it's just 6 indicators in this case, and you can see the weights. The last 2 are quite low weighted compared to the others. If we look at the times, it's kind of different. You've got 5 dimensions. The first one is teaching, and it consists of sub-indicators, so there's actually more indicators that go into this. That's given 30% weighting. Research, another group of indicators, is also 30% weighting. Citations, 30%. And then you've got international outlook and industry income, which have small weights. Whether you agree with those if that agrees with your notion of what a good university is or not, I mean, that's what it is underneath, okay? So we can look at these rankings. You can download all the data, and you can start off just by looking at scatter plots. If you look at, so this is just the 6 indicators of the QS rankings, and each of these points represents a university, okay? And you can see, I've taken the top 200 here, by the way. You can see the kind of distributions you have, not terrible distributions, but some of them are a bit skewed. And then there's some correlations, like if you look in the bottom corner here, you can see a kind of correlation between international faculty, international students, which kind of makes sense. If you look at the times, again, some sort of not terrible distributions at all. And then there's a very strong correlation between research and teaching, much stronger than the rest of the correlations, okay? Or dependence, I'll use the word dependence. So actually, before we look at sensitivity analysis part of it, it's interesting just to plot the 2 rankings against one another, because they claim to measure the same thing, the kind of quality or excellence of a university. And you can see, if we plot the Times ranking against the QS ranking, and of course these dots represent universities, that there's actually quite a large disagreement between the 2, particularly as you get into the higher rankings. And these differences can be quite large. If you look, so this is basically the difference in the 2 rankings, the absolute value of the difference, sorted by the Times ranking. So the left side is the highest #1 ranking, let's say. And I just picked out some universities some points that stuck up quite a lot. And it tends to be, for whatever reason, like all the University of California parts are really ranked a lot lower in the QS rankings than the Times. So all of these marked universities here represent universities that are ranked higher in the Times than the QS. And if you look at, for example, Ulm University, and I don't know if anyone's from that university, probably not, it's actually 200 places lower in the QS rankings than the Times. So it just shows there's a lot of uncertainty, okay? If we get onto the actual regression sensitivity analysis, so I can fit all my different regression methods through these university data. You can see it's not hugely nonlinear. There's a little bit of nonlinearity, maybe, and the fits are quite similar for the most part. With the Gaussian process, we get a quite nice property because, again, using this MCMC approach, we can take samples of the main effect, which represent the uncertainty in the parameters. So this is the mean function of the Gaussian process, and the variation you see is from the parameters. It's not the same as the confidence intervals that we saw before, because they actually represent uncertainty in the data, which is different. And the nice thing I like about the Gaussian process is if you look at the top left of the green lines here, you can see that it's kind of got like a wiggly fit, and then there's some fits that go quite smooth. And if you look at the top left plot, in the very top left, you can see the different methods. One of them has this wiggly fit, and the other one has the smooth fits, okay? So the Gaussian process kind of encompasses both points of view. So I think it's probably the most flexible of these approaches. And then you can get these histograms of sensitivity indices, which I'm not going to talk about a lot, but there they are. Then you can look, okay, so I didn't show the actual values of the sensitivity indices, but here they are, and these are compared with the weights, which represent kind of our targets, okay? So the blue values are the targets, and the red values are what we observe. And you can see that, for example, academic reputation is quite well matched, but employer reputation is much higher, has a much more importance than it should have. Whereas, for example, faculty-student ratio and citations per faculty are much lower than it should have, okay? And then the other two are not bad. We can do the same with the times. We get the same kind of things, some non-linearities. You can see there's some quite strong dependence in some cases. Gaussian process, again, gives us some confidence intervals. We get use the fits to give ourselves histograms. And again, when we look at the difference between the target importance and the actual importance, then we find that in this case, citations are actually undervalued. Industry income is about right. International outlook is quite wrong. And research and teaching are a bit more important than they should be, okay? So that's the first thing. Now, if we go to the sort of third tool that we looked at, which was the optimization, we can see what happens, or we can try and find the weights that actually adjust these to the right importance. So the green bars here are the target importance, the one we want. The red lines are what we've measured using the weights that they use, which you can see are different from the green. And then the purple ones, the light purple, is the optimized weights using the optimization algorithm. And you can see that the light purple is always the same as the green bars, so the optimization's worked, okay? The other thing you can do is constrain the optimization so that all the weights are positive, or zero or positive, like not negative, right? If you do that, you can't really find a particularly good solution in this case. Because, for example, if you look at the employer reputation, you can see that the dark purple bar is much bigger than the green bar, which means you didn't really get the right importance in that case. If you look at, so these numbers here actually represent the weights. The green is the original weights, and then these are the different optimized weights. You can see that what you come out with is actually negative weights in a lot of cases, because you're trying to compensate for these correlations. And you need to adjust your weights quite drastically to make them match, okay? So using these negative weights, in some cases, I actually get the right answer. If I constrain it to be positive, it sends some of these weights to zero in an attempt to get the right solution. If we do it with the times, it's similar. we can use the unconstrained optimization, and we end up with a small negative weight, 0.08, minus 0.08 in one case. But if we constrain it to be positive, and the reason that you would do that is mainly because it looks nicer, really. And that's it's quite a big concern with composite indicators, because ordinary people are going to read this, and if they see negative weights on some things, they're going to think, what's this all about? But if at least they're positive, that's one thing. Okay. If you constrain it to be positive, you can actually get quite a good solution. So you can see the dark purple bars here actually match very, very well. And what this tells you is that if you set the research weight to 0, so effectively you remove that indicator completely, you actually get the kind of importance that you want, because the research indicator is already contained in the other indicators. So it's kind of redundant in a sense. These are like more detailed results. I'm not going to go into in any detail, but just to show you, so this is just showing the different methods, the estimates in terms of the total SI, the correlated and the uncorrelated parts. Just 3 quick points. One is that, first of all the 3 methods tend to give you similar answers. But if you look at the difference between linear and non-linear, in some cases it's significant. Often it's not that different, but in some cases it is. So it's worth using non-linear regression. The second thing is that in a lot of cases, the uncorrelated part of these indicators is a lot more, can be very dominant. The correlated part can be dominant over the uncorrelated part. You can see an example here and a more extreme example here, where actually almost, and this is the research variable that we ended up discarding because all of it's encoded in other variables anyway, so you could just get rid of it. So if we then say, okay, let's assume these we accept these new weights, and then we can plot the new rankings against the original rankings. So it's the same, just in both cases, the QS ranking here, but one has the original weights and one has the optimized weights. And this just shows the scatter, okay? And maybe out of interest, you can see what the top 10 would look like. So some interesting changes, good news for the University of Illinois, which is now 4th in the world. Some universities jump up the rankings quite a lot, like also Johns Hopkins, Duke University. Some go down, which I haven't shown. Do I claim that these are the real rankings? No, I don't claim that. All I'm claiming is that if you assume that's the importance that they assign, which I think it's what they want, and you use their methodology, that's what the answer you get. But there's so many other uncertainties in it that I wouldn't claim that these are the real rankings. But I think it's interesting to see what happens. And you can do the same with the times. You get the same kind of scatter. And in the case of the times, the changes aren't quite as drastic. But Johns Hopkins jumps up. Nothing really quite as significant. But if you go into the lower rankings, it does change quite a lot. So you might argue that the times is a little bit more robust, maybe a bit better. So conclusions are, overall conclusions. First of all, the fact that weights don't equal the importance in composite indicators. So that's something to take into account if you ever start delving around in these things. Sensitivity analysis can help us to explore. And the reason I'm doing this is because I have a kind of background in sensitivity analysis, and now I'm working in composite indicators a bit, so I'm kind of trying to see what I can do with both tools. And I think there might be other things you can look at as well. Rankings are really sensitive to assumptions, very, very sensitive. I haven't explored things like the aggregation method, the type of indicators you include, and so on. There's many, many assumptions that you can look at. And then a couple of open questions. Does importance really equal SI in this case? Does that really summarize what a person means when they say that this is an important variable and this one isn't important? That's something to think about. And another thing is, we kind of assume, in a way, that when people assign these importances, they're not taking correlations into account. But maybe they are. Maybe when you think that research is 30% important, you've kind of somehow implicitly in your head got an idea that it's correlated with other variables, just from life experience or something like that. So there's kind of like there's plenty of caveats, basically. So that's the end, and I just wanted a few references on different subjects if anyone's interested in that stuff. So thank you very much.
Thank you, William, for this interesting presentation. I think that people here is not very aware about these tools, composite indicators, and it can be helpful because I think it can be interesting for people who are using models with several outputs, and they try to merge everything into. So we have time for questions. Okay, Andrea?
Yeah, thank you, William, for this very interesting and thoughtful presentation of all these results. One thing I'm wondering, you kept repeating to people, over and over, we all know that weights don't mean importance. But I think this is not such an easy concept to grasp.
Yeah.
So I would, I don't know, I don't know what your impression, but probably I found often difficult to have this discussion with people because it's something you learn by looking at the results. No? For instance, if you don't show someone a scattered plot, he will not believe that a variable with a larger weight is not more important than one with a lower weight. Then you really have to show these things. So this is an element. It's important because otherwise people believe that all this is, everyone knows this. In fact, I don't believe that everyone knows it. And the other things, the effect of correlation is even more subtle because in a sense what William was saying is that if you want, in a sense, to cheat the system, not only one way of cheating the system is to play as to improve variable in couples or triplets, Because if you do that, you increase your ranking, as you have seen, because the shocking differences which you have shown on some university was possibly due to this, most likely due to this covariant structure, So you can really play of your covariant structure to increase your ranking. I would say that this is rather, subtle ideas, not so easy to immediately everyone understand them.
To agree, yeah.
Just a comment.
Thank you. Other questions? Okay. I may have one question. How do people, you show that when you use this kind of optimization without constraint, you may find negative weights.
Yeah.
And if I remember well, people do not like this kind of weight, right? But what if you, in this case, you just inverse the values? In the sense that the high values of this indicator become the lowest, and so on. To change, is it a possible trick?
Yeah, you could do that. Yeah. But again, I suppose that's probably in a way the best way to do it. But you'd still have to. It would still be obvious at some point in your methodology, that for example, I don't know, let's say research, that you've now weighted it so that universities with better research actually go, are penalised. So if someone's kind of looking into the details, they might say.
Yeah, but they don't see actually what you did with the data when you for instance, when you have your variable and then you standardize them, right?
Yeah, you could just flip it around.
Then, okay, so it's just values then, and it doesn't really. It's not really easy to read, right? Yeah. So you can do whatever you want. You can, for instance, inverse the invert the values. The highest value becomes the lowest one, and so on. This is your choice. I mean,
I think in some ways that would be the best solution. But in general, it's quite difficult to sell any weights that are different. If you have equal weights, or you have like 30%, 40%, then that's one thing. But if you start saying, well, we need 0.3 here, and we need 0.7 there, and 0 there, people are just going to question where all these numbers come from. And you can't explain to a lot of people, that don't have a bit of background in statistics or whatever, you can't really explain why that is to them very easily. And that's like a common, that's just a really prevalent problem in this kind of work.
Okay, thank you.
Compromise.
No questions? Okay, so thank you, William.
Thanks.